Okay, why water quality? Yes, apart from drinking, we have to do some fishing, bathing, navigation. We know that every coastal area with sunshine is a full of attraction for tourists, so water quality is very, very important. But let's look at what we call clean water. Yes, some of these on the right-hand side were sort of photographs I took from the north of Scotland. No, just from 30 miles from here. From the catchment around, you would say that this water is really clean. This is clean water. So what happens when we have buildings? This is what happens when rain falls. It goes into the ground and goes down. But when you have an urban area, you have actually consolidated the soil. So rain falls and a lot of it will run off. And that runoff will take whatever you have put on the soil. Just have an example here. Here is cars. You have got cars going around. This is what happens when you have stopped water from going into the ground. This water falls here, it has to go somewhere. What is the quality of that water? Just to give you an example, this is the work we did here at Abertay, looking at what is the pollution from cars. If you look at, this is a car, this is the total load in the UK. So you've got lead, copper, zinc, just by just driving the car. When you wash the car, you've also got some other pollutants there. So, car pollution, vehicular emission brings about water pollution. This is also a work we have done at Abertay here. We have rain water going from the roads going in there. And we have to take samples to look at what are the level of pollutants there. You can see we have got oil, nickel, copper, arsenic. So the roadside swells are actually a source of pollution. And if you have a little stream around here, it will wash this off. But something is happening here. These are more examples. In fact, this photograph, I took that in Brussels a few months ago. This is sort of an inland pond, and you've got all growth on top of it. It's because of pollution. And this is why pollution, mine drainage pollution. And more examples. This is underground petrol tank. You go to take fuel, okay. But that could be leakage. That means the underground water can be contaminated by this. So this was dug out and realized that you have a lot of leakages, and this will go directly to the groundwater. This photograph I took in the late 90s, I think early 90s I would say, in Paris when I was looking at the pollution from buried waste. And what you've got here is the water from waste that is buried there from a landfill site. So if this water is allowed to go to the groundwater, you would know what happens. This is Villeparis, very close to Charles de Gaulle Airport. So what we're talking about here is that we have human-induced pressures on water quality. And everything we do produces some sort of pollution. And that pollution might end up going to the water. So what do? We try to break that link. But we cannot stop this from happening. So what we do then is, because we have, the challenge is not to do nothing. Because if we do nothing, that means we have a lot of problems with our lakes and groundwater. So we have to clean up. But the cleanup, is there anything we can get out of it? We could. Let's see. How can we solve the problem? Just bring back this slide. My colleague Andrew gave me this slide. This is where the runoff from the road goes into. And we took some microorganisms here and realized that these microorganisms actually live there. So these microorganisms are breaking down these pollutants. And looking at it, this is an example because it does. We could go more high-tech by encouraging these microorganisms and feeding these microorganisms with some other things. So, but the more high-tech you go, the higher the capital cost. This is more efficient than this. This will take, they can do the same work, but within a very short or long time, depending on the technology you're talking about. So, what is the challenge? What do? We have to try to look at these processes that will reduce these pollutants into very small before it goes to the water. And this is, I'm just using the biological process, a very complex thing, because the microorganisms that require different environment, different things. So it is a complex situation. So what do? My research then is, how can you engineer this natural process to prevent aquatic pollution and to recover any valuable resources where they exist? So I'll just give you some few examples. These are some of the sources of waste that we inevitable. We always have to produce everybody. The industries, we have ice cream, we drink whiskey, we drink Coca-Cola. They all produce byproducts. So we are always producing this. We have also the domestic waste that we produce called sewage. If you do nothing, you have this fish. This is an example of fish dying because you put these pollutants into the water, and during the breakdown, oxygen goes away, and the fish do not have oxygen to live to die. Alternatively, you could also have, or in addition, something like this, where this water is covered by this vegetation. As I said, I took this in Brussels, just 2004. So it is what is common in most places. So what have been our work? As I said, it's pollution control and resource recovery. And we introduce anaerobic processes, which is a process that we have developed and enhanced at Habitat through the work I do. And that's where I have my specialties more on. Which is basically, what we do is we have these microorganisms here. We do really not select the microorganisms. We allow the microorganisms to flourish depending on what we add into that. But the key thing is that there's no oxygen. So the waste goes in here, but it breaks down the organic carbon that would have caused devastation in the rivers or lakes, but it also produces other byproducts, like this is energy, and this is fertilizer. So the energy part is methane gas. This is what the equivalent is in terms of energy production, which is very, very important. So look at the soil coming out of it. You can use it to grow, just like compost. There's some trials we've done. So this process is not as easy as I've just said. There's a complex process. However, it comes from a natural process. Look at this cow. This is what happens. This happens naturally in a cow. Those three stages I told you about, we looked about the previous slide, are all like this. This is the breaking down, the making it wet, fermentation, getting it, and then producing the gas. Obviously, you do not get some light cigarettes behind a cow, but problem is, because the cow moves out in the open, obviously there's dilution in the air. However, it's not going to be the same problem if you have a cow shed that is covered. Okay, so that's where you have to be careful. So we try to replicate that process into this. And we developed this technology at Habitat, where we developed a system that selectively partition these microorganisms in various areas. What we're trying to do is to maximize the rate of conversion in order to make the system work faster. And that's what we produced this. And we tested this product at Tennent's Brewery in Glasgow to show how we go from the lab to the industry. And it was a very successful test. The second example we did was we looked at ways of reducing a particular pollutant, they call it organic carbon and nitrogenous compounds. Instead of having this done in these three systems, we developed a system where they could be done in two. Obviously, it's cost savings, and that's by finding some pathways. These some biochemical pathways, which my first work in 1992 came up. Okay, and since then, we have got about over 1,000 citations on that process. To give you an example of the development we have done in that area. So, because we can now transform a lot of these pollutants into some other sources, whether it's energy or fertilizer, then there has been a boom in the last few years of trying to maximize this energy production, it's called, and take advantage of that. So instead of using the technology for this only, it is now extended on various other areas that people are using purposely to produce energy. I'll give you some example. Crops are now grown to produce biogas. And these are maize, sorghum, and they're shredded in this form. And there used to be biogas plants. There are so many of them around now. There are so many in Germany as well. So what are the challenges of these new things? So we need to develop new microorganisms, new pathways. We need to try to use mathematical systems to model to predict how these things work and to predict when there is inhibition or when the feedstock contains things that can kill bacteria. So that is that. And finally, to train researchers and people who are going to man these installations. And that's what we do. I'll just give you another example of something that we very close to what we do at Abertay, using feedstock that is very close to us here, and that is the seaweed. Everybody knows what seaweed is. It's all around the place. In the UK, you have the seaweed in all coastal areas in the UK. However, the seaweed has a problem in terms of microorganisms. It has high salt content, and it also has phenolic compounds, and these are things that some microorganisms do not like. So we need to find barriers. How do we remove these barriers that would so open up this biogas production using the seaweed that is produced naturally? The sea is huge. There is a lot of room for planting or having enough feedstock for AD systems. We found out this is very much complicated, but what is here is that the phenolic compound that is toxic. This is the work we did here a few years ago, just 2 years ago. This is my PhD student. We realized that this particular compound, which we extracted from seaweed, blew up the cells. These are cells that have actually destroyed. So we are comparing that with water. You can see what it means. We also were able to try to use mathematical systems to model how this toxicity is going to affect the growth of the production of methane. And this is some of the work we did in terms of modeling. What you've got here is the model prediction, and this is our experimental. You can see how well some of the things the mathematical tools we produce here at Abertay. So, to come to the final and to give you some very common highlights, which you might not really be associated with pollution control, but they are here and being used. Look at this. When I talked about being very careful of how you take open flame close to a cow, this was just reported 2 months ago, in January, where German cows caused methane explosion, right? So you have to be careful not to do that. And the second one is these scientists from Argentina. They have developed a system where they attach some tube behind the cow, they move around, harvest the biogas up there, and use that to power their cars. Yeah, but this is kind of funny, but you could, in a few years, in some countries, see a couple of cars with some backpack, but that is energy. You see, this is also in the UK. We've got this human methane-powered car runs on human excrement. What it means is that you have got this pollutant coming up from human waste that is converted to energy, and that is then used to produce that. But that makes a good headline to say human excrement. They did not put it in the car engine. So this summarizes the talk I'm giving today, which is wastewater resource recovery materials. So you can recover organics, recover energy, and recover nutrients, and nutrients in terms of fertilizer. And finally, you can also return water. In many countries where, like the Middle East, where you do not have fresh water, why do you want to throw the water, the flush your toilet, into the sea, where it is more difficult to get it out? You can see that the freshwater reuse is actually a very, very important in terms of irrigation. Look at another one. Food waste powers UK sewage treatment plant, and this is just quite recently. This is in Birmingham. Fine, you have the food waste coming, sewage treatment plants. You have all sorts of materials you can recover from this. Look at this. And finally, you have something like this. This is humic acid being recovered from water treatment sludge. And these materials are actually quite expensive. You can see that. So the drive now for wastewater treatment or pollution control is also the drive to get materials out of this waste. And just last week, there's a workshop in England where they were talking about turning wastewater into revenue. And these are things there. And this is for producing energy, and the other one is for producing fertilizer. So, to conclude, I think what I can say is that I think I've convinced you really that uncoupling the link between water quality and human activities is very, very possible. In fact, it is something that everybody should do. Is it costly? I don't think so, because you can also recover materials from that. Thank you very much.